this thing that when you deploy a model in the real world and it's out there churning out predictions day after day and year after year, the data on which it's being trained is going to change, and the data on which it's making predictions, that input data is also going to change. Why? Because the data generating mechanisms might change. For example, the behavior of the people who generate the data, for example, if you're taking people clicking on ads, right? People's behavior might change in 3 months. So, how do you deal with drift in the data's properties? That's the second point I would like to emphasize on today. And the third one is on the importance of feedback loops. So, very often when people talk about training a model and deploying it, they think of it as a one-time activity. Right? I do all my security data analysis and train my model, and then I deploy it. Now, after deploying, what happens? Right? How do I generate new data to retrain my model once in a while? So, training the model works when you have a supervised training system, supervised learning system. Right? What do I do in an unsupervised learning scenario? Right? So, feedback loops become very important there, and that is what we discussed. Let's start with accuracy versus interpretability. Take the example of demand forecast itself, which I mentioned earlier. Right? Suppose I go and tell my company and the revenue department of my company, or take the supply department of my company. Right? So, suppose I run shopper stock, and I need to figure out what to stock in my warehouses. I go and tell them that, hey, your demand is for this, and this product is going to be so and so, and you need to put that in the warehouse this month. That's very valuable. So that's the first column we have here. Right? This column. So for supply planning, if I give out a number saying that this is the demand, that's going to be very useful. Right? But suppose I work with the marketing or sales department of Shopper Stop, right? And the data scientist comes and says your demand is going to be so and so next month. I'm not interested. What I'm interested in is how can I increase my demand. If my demand is going to be lesser next month, why is it going to be lesser? Right? And what actions I can take in order to increase it. So depending on who your stakeholder in this matter is, what output you produce also changes. And that's not very often discussed when people talk about machine learning. People think that machine learning is about making predictions. It's not always about making predictions. It's also sometimes about understanding the underlying reasons for why those predictions are. Take another example of churn itself, right? Suppose I'm working in the marketing department of a company. It's not enough for me to know who will churn or who will leave my so say I'm again Shopper Stop, right? I'm working in the marketing department of Shopper Stop. It's not enough for me to know that so and so person has left Shopper Stop. He's no longer interested. I also need to know why did they leave Shopper Stop? What can bring them back? Right? So again, if my model is only good enough to make a certain prediction saying that this person with so and so probability is going to leave Shopper Stop. They are not going to buy from you anymore. Right? That is not enough. What is needed is my understanding of why did that model make that prediction. So tractability of how a model is making predictions is very important. This is not in traditional sections of marketing and demand forecasting and stuff like that alone. Right? Take an example of say topic modeling. You want to know what your customers are talking about. You're following their social media and you're scraping their tweets and identifying topics from that. And what are you going to use that for? You're going to use that for identifying what are your customers' interests so that you can engage them better. It's not enough to know what words fall into what buckets, right? Because ultimately a topic modeling system is going to give you a bag of words. That's what it's going to give you. Now, does that bag of words correspond to some topic? If so, what topic is that? Right? There's some intuition that has to go in there in order to identify that. Today, probably it's done manually, but if you're making a model do that, what I want to point out is that the thing on the right hand side is what's more important than the thing on the left hand side. So, what are my customers talking about? They're talking about Colgate toothpaste. They're talking about this. They're talking about that. But what does those 5 words they are talking about together mean for the customer's persona? That is what. So, in this thing about interpretability versus accuracy, there are situations. What I want to point out is that there are situations where interpretability is more important than accuracy. There are situations, right? And one thing to keep in mind when is take it with a pinch of salt, right? Take it with a caveat that interpretability is no longer it's not valid when your model is not accurate. Let me explain that a bit. So interpretability is great. It allows you to take actions. But suppose I have a very, very interpretable model that has really bad accuracy, right? It has large errors. Then what am I interpreting from that model? Because only when a model is accurate enough is it a good representation of how the real world works. And only if I have a good enough representation of how the real world works, how my customers are behaving, how my revenue is going to move, only then is it, as a next step, valid for me to ask why does it do that. So, as an example, I was working recently for a company that deals with pharmaceutical data, and they were interested in understanding why do people stop taking medicines that for chronic diseases, say asthma, right, or say certain long-term diseases like AIDS, right? Why do people stop taking that medicines, even though it may be covered by medical insurance and stuff like that? Right? The model that they were using currently, that was very, very interpretable, right? It was giving results. These are the 5 top reasons, but accuracy was like 30%. Okay, the error was like 70%, and what I was telling them was that, hey, you cannot trust the interpretable results that you have got if your accuracy is not good enough. The reason being that it's not modeling what is happening out there in the real world. And only once it does that, only then you can ask the question, what are the factors leading to that? Is it clear? Another situation where the accuracy versus interpretability debate becomes important is in situations where you have a large number of decisions to be taken versus the cost of a wrong decision. Take the example of Amazon recommendations. What if Amazon makes a wrong recommendation to me? See, it says, buy this book. I don't buy it. That's all. Right? Not a big deal. So, when in situations like this, where the number of decisions to be taken, because the Amazon customers are like into probably more than millions, right? So, when the number of decisions to be taken is very large, but the cost of a wrong decision is very low, you can automate a thing, just like Amazon has done it. And you don't really need to understand why the model is making a prediction, because even if it makes a wrong prediction, it's okay. Nobody's losing anything large. Take another example of, say, I'm sitting within Morgan Stanley or Goldman Sachs, and I'm a trader, and there is a system within Morgan Stanley or Goldman Sachs that recommends what stocks I should buy, right? And I'm buying that stock with my client's money, right? And I'm buying in millions. Imagine that system and think about what is the cost of a wrong decision there. When that system makes a recommendation to me saying buy so and so stock, the first question I ask is why. And there, model interpretability becomes very important. I would want to understand why the model is making a particular decision. There are other systems like these, which are again totally out of the way, right? Because in self-driving cars, the number of decisions to be taken is very, very large, and the cost of wrong decisions is also very, very high. And that's one of the reasons it's a very tough problem. Right? You cannot put a human in the loop. It's not easy to do that because the number of decisions are large, and you cannot have a low accuracy model because the cost of the wrong decision is high. Dealing with data drift. So what exactly is data drift, right? Let's look at what causes data to change. So, and before that, let's look at why is it important if data changes. So, once you train a model and you deploy it, what do you do then? You let the model run and make predictions, right? Or recommend actions for you. Now, the model has been trained on a particular data set, and that is the that basically has given rise to the particular set of patterns that it recognizes, and it generalizes to a certain kind of data set. But what if your data really changes by a large amount? The data can change if the underlying process that generates the data change. For example, you give certain discounts and people's buying behavior might change, right? Your competitor sets up a store next to your shop and people's buying behavior might change. You can always say that I can take into account these things, but it may not be possible to quantitatively take into account a lot of these things. So one has to understand that you have to change your model basically, because your model is no longer able to predict well because the data on which it has been trained or the data on which it's making the predictions is changing. It can also happen because your data capture systems have changed. Imagine that you are doing a software update and certain fields are now no longer available, right? Suppose you do your data entry through or your data collection through Salesforce, right? And Salesforce came up with an update, and two things that you used to get, two fields that you used to get captured in your database are no longer getting captured, or another new field got introduced. Your data structure has changed, and where data was being captured and now is not being captured, you might get missing values. So your data content also has changed. The other scenario that you can think of is your measurement systems themselves have changed. So the errors that are inherent in measurements, right? They are caused by two things. One is the process of the measurement itself, right? I measure something with a very accurate ruler and I make a mistake. The second is that my apparatus itself might be faulty. Right? The ruler that I'm using or the temperature sensor that I'm using is slightly off, but I don't know that it's slightly off. Suppose I replace my temperature sensors in a boiler and I'm running a factory. Now the new sensor is giving better results, but your model has been trained on the old sensor's data. So, given that data drift happens in the real world when model is deployed, what do you do with it? How do you deal with it? First thing is detect data drift. For this, you need to have modules, which is basically code, right? That run statistical tests on the data and identify changes in the behavior or the distribution of data, right? It could be identify outliers, it could be identify changes in the median, whatever, changes in the quartiles, whatever. Right? And these have to be run at regular intervals to make sure that the assumptions that ought to hold for your model to make predictions, they hold. Like, if you have a linear model, basic assumption is rough Gaussian. Your y variable or your outcome variable should be roughly Gaussian distributed. Now, suppose that drastically changes, you should be able to detect it. Another thing that you could do is detect missing values, right? Or this missing value detection is again identifying structural changes in the data. So you have to do two kinds of things when you say data quality check, right? One is identify structural changes in the data. One is identify statistical changes in the data. In addition to data quality checks that you have to run, you also need to run model quality checks. Right? So you need to be able to, again, we'll come to this in a minute, but you need to be able to collect feedback and say that the predictions that my model is making is no longer relevant. So my model performance is degraded, so I should update my model. Okay. Now, who's going to do these checks? In deployment, you should have, you can call it subroutines, modules, whatever, right? You should have pieces of code that run and do these checks at a regular interval if you want to keep track of how your model is performing. And once you find that your model performance is degraded, either because of data quality issues or because your model is no longer relevant for whatever reason, you retrain the model. That's one way of dealing with it, right? Now, suppose you retrain the model and find that still, it's not giving great results, and you need something to fall back on. You should have fallback options available. So when you design a machine learning system, you don't design one model, you don't train one model. The key idea is that just like you would do it in software development, right? You have fallback options. If something fails, something else should take over, right? And that fallback option can be a human system, like it could be an analyst, or it could be a rule-based system, or it could be a simpler model that has less stringent assumptions, which still hold when a lot of other assumptions have gone for a toss. Just mentioned feedback loops a bit right now. I'll get into a little more detail about that. So this is the typical data science workflow that you'll find in books, and you will see people talking about and stuff like that. So there are two phases here. One is a prototype phase where you build the data science or the machine learning model, and the second is the production phase where you deploy it. In the prototype phase, you have the data, you clean the data, and you extract relevant features, and you do exploratory data analysis and all that, and you train the model. And you test the model based on various techniques that you have available. Right? You can look at various metrics, or you can do cross-validation. You test the model, and your model may not perform very well. So you do more exploratory data analysis, EDAs for exploratory data analysis. And you come up with more meaningful features, which you give us input to the model, treat the model again. That's an iterative thing. So this part here is a very iterative thing. Right? And you come up with a certain model that you are happy with. Once you come up with that particular model, that trained model, you deploy it. That's typically how the data science workflow is portrayed as. Right? What I would like to point out here is that this is great, but it's not complete. Let me try to indicate why it is not complete. Right? This works great for a model that can be trained for supervised learning. What do you do when you have an unsupervised learning task? This really is not the workflow for that. Right? How do you even test it before you deploy it? So let's consider these questions, right? What about unsupervised learning systems? Second question. I said data is available to train the model. Where did the data come from? Right? And is the data going to be just sitting there, or is the data going to change? Is new data going to come from? Is new data going to come in as the model is being deployed and is working for a month? There must be new data, right? Where is that going to come in from? Even if you have data available to start with, how are you going to test your model in an unsupervised setting before deploying? The answer, I think, is feedback loops. Let me illustrate that with an example of how the data flow happens or could happen in an unsupervised setting. We'll get into a little depth about how the data flow happens and where the data moves between various components in this picture. Consider this, that you have your database, simple regular database. Right? X is your input data, and Y cap is your prediction. That prediction could be a recommendation, or it could be an anomaly, right? An outlier that is detected. That's again an unsupervised task, learning task. When your input data comes in, and you have this unsupervised learning technique that's you could use potentially, and you have your end users who are so whatever recommendation or anomaly is detected, that's fed into the end users. They are the consumers. Right? So let's look at how the data flows here. Input data comes in, and so before we get into input data coming in, just wanted to point out one other thing. You have a certain set of X data, input data, historical input data, and you have a certain set of recommendations or anomalies detected or whatever predictions that you have made using that input data. Right? You do not have labels, you do not have actual values, which is why the task is unsupervised. If it is a supervised learning task, you would have the Y values, and you could test your Y cap, which is your predicted values, against the Y values. Right? But since it's an unsupervised task, you do not have the Y values. Now, and your unsupervised learning technique has been, uh, you have developed this technique based on this input data, okay, that you have. New data comes in. What do? You send that to your database, first of all. Okay. You also send that to your unsupervised learning technique, which in turn produces recommendations or anomalies and gives it to the end users as well as updates the database. So this is, until here is what we saw in the last picture, the equivalent of what we saw in the last picture for unsupervised case. Right? Now, what else? Where is the feedback loop? Without this feedback loop, how would you have calibrated your model? And very often, when you have unsupervised learning techniques, if you develop a model based on whatever data you have and deploy it, it's not going to work very well or very efficiently or very accurately without continuous improvement. And where is the continuous improvement going to come from? That's going to come because you're going to get actual responses from the users about whether this recommendation was useful or not, and then calibrate your model based on that. How would you do this in practice? The way you would do this in practice is by putting up a very lightweight feedback loop. You do not have to do a Spark data engineering pipeline or anything. You could be a Shiny dashboard or something like that, right? In a simple 2-day effort. But the key thing is this: that your recommendations should go to the end users right from the beginning, and they should give you feedback right from the beginning. That way, you'll be able to continuously calibrate your model as your system is running, right, and improve it. The same thing works in the case of supervised learning scenarios also, and your feedback loop there would look like this. So in this case, you have x, y cap as well as y. Y is the labels that you have. And the train plus test part is what you have used to train your supervised model. Input data comes in, goes into your database. It also goes into the trained model, which makes predictions. And once the predictions are received by the users, you need to collect feedback from the users. Otherwise, your new Y labels are not there. Right? If you do not collect new Y labels, how are you going to train your model next time? So, yeah, that was about the importance of feedback. Throughout. And in unsupervised settings, unlike in supervised settings, you do not have a cross-validation kind of scenario where you can say that I trained my model and tested the model on data that it has not seen. That's not there in an unsupervised setting. So that level of confidence you cannot get. So the best way to deal with an unsupervised scenario is to create that lightweight feedback loop and start using it right from the beginning. I think I'll stop there. Thank you. And so we are hiring. So if people are interested, we can have a conversation.
This supervisor data, this supervisor data can be trained by deep learning, that is feedback loop.
Deep learning is a model again.
In the feedback loop has to be through the deep learning.
Not necessary. So think of it this way, right? Deep learning. So whatever we talked about now is basically what else do you need apart from a model in order to have a good machine learning system, right? Deep learning, just like decision trees or linear regression is another model. There are several things, some of which I listed here, that are needed in addition to your model in order to have a good machine learning system. Right?
But supervised data is more imperative. So it has to be the training that one needs the
Not necessarily.
The data drift is more. The time to respond is not.
Yeah. So that's very subjective. So if you take, so that basically depends on how fast your data is changing. If you take, suppose you're Google or Facebook, right, and you have to show ads at millisecond scale, and your customer, you're dealing with so many varied varieties of customer bases, customer segments that they can rapidly change also, right? One customer segment might drop out, and another might come in. In that case, you'll have to be very, very fast, and you'll have to continuously check the whatever the distribution changes, or has my customer segment changes, have new customer segments come in, all that, right? But suppose you are say again Shopper Stop, your customer segment is not going to change very fast, right? Or say you run a grocery shop, right? People who come from the neighborhood to your grocery shop, they are not going to suddenly go to the whatever next neighborhood grocery shop just like that, unless some drastic thing happens, like your competitor sets up a shop nearby or whatever. So basically, it depends on the use case that you have in hand, and that will determine how fast your data drift happens, and that will determine the rate of retraining your model. Example of?
Automated car.
Yeah.
So the data drift is always there.
Yes.
So the time to respond between electronic and human.
So, yeah. So first of all, I think in the case of a self-driving car, it's not a supervised learning system or an unsupervised learning system. I think it's a reinforcement learning system. I've never really gone into the depth of that, but it certainly is not just supervised or unsupervised. So whatever I said here is for your run-of-the-mill everyday applications of machine learning, which you would end up doing most often, right? How often do you get to work on a self-driven car? So in a self-driven car, the techniques might be very, very different, and it might not even be retraining, because in reinforcement learning, that something equivalent to a retraining, that you move closer and closer to a certain objective, that is happening continuously. That is the reinforcement that's happening. So that maybe that's being taken care of there. That really quick data drift over there. Any other questions?
I think that so the static label data table has to be initially created.
Yeah, you need data to train the model, right? So where does that data sit? I showed a table, but it could be anything, right? It could be a flat file, it could be an Excel sheet, anything. It could be an HDFS, whatever.
I have a question regarding the feedback loop for unsupervised learning. So if you take an example of, let's say, customer profiling, and we are creating some kind of clustering, using some kind of clustering techniques to create the customer profile, what type of feedback will be sent back to the data set?
So who's the consumer there? You create the customer segment. Who's going to consume that insight? Yeah. So the marketing team would say probably that. So let me put it this way, right? The example of customer segmentation is not a great example to illustrate that. It's unsupervised. You're right, because you don't need to create or look at customer segments every other day, right? You create it once in a 6-month period and use that, right? So if you look at the picture, your predictions are going how many times? These Y cap. When new data comes in, are you going to recreate your customer segments? Not necessarily. So this picture is for a system where the number of predictions are going to be frequent. Like imagine a situation where you are running a factory and you have sensors, right? And you want to know if your boiler is working correctly, so you take the sensor data and identify anomalies in the boiler temperature, right? That is a system that continuously is monitoring the boiler temperature and flagging anomalies. So X data is coming in continuously, and your anomalies are continuously being given. As and when they arrive, they are continuously being provided. Okay.
Just a question. How is anomaly detection unsupervised learning?
It's outlier detection, right?
Yeah.
So what are you training on?
So you will be training, so mostly I thought for anomaly detection you will train on the good data, whatever is an anomaly you will train on.
No, if you are doing it based on a reference distribution, you can create a reference distribution and look at outliers in the distribution, right? So you're not training a model because there is no equation there. You create a reference distribution which is basically based on this data, and say that outliers in this distribution I'll got by anomalies, simple, right? But similar to this situation, what is your y and x relation? What is the equation there? When you have a supervised learning mechanism, what you're doing is that you're training the model to recognize that for a given x, this is the given y, or this is the y value, right? There is nothing equivalent of that over here. You're creating a distribution of what the x values are and looking for outliers in that. You're not training any equation. Okay? And your customer segmentation example, that may not be a great example for this case because the feedback loop really makes sense when you want quick feedback, right? Or when you want your system to tune very fast. Okay, suppose you do a clustering and you're going to use that cluster for 6 months. You show that to the marketing team, and the marketing team says the cluster is okay. You don't need to touch it for the next 6 months.
That's one more question. In this case, it's like in this anomaly detection, while it can be tested and see that that tested while values are part of its distribution or not.
So what is y here? Y is a flag in the case of anomaly detection, saying that is it an anomaly or not. X is your data, that is a distribution, right? That's distributed in a certain manner. If it's a temperature, it might be Gaussian distributed, simple example, whatever. Okay. Now, y cap is your predicted flag, saying that I predicted this as an anomaly or not, right? Then what is y? Y is decided by the consumer, end user, saying was the prediction right or not? Was this actually an anomaly? Is that sorry, can you repeat what you asked?
Why can't we have a training and test for anomaly in this particular case? If we have let's say some test set of data, for which we already know which are the anomalies.
You can. Then you would not use an unsupervised learning technique. You would use a supervised learning technique. Yeah. You can do that if you have that.
Sorry. Yes, sir.
Okay.
Suppose we are looking for a cybersecurity prediction or a attack prediction using machine learning technique. Suppose in the case of a DDoS attack, such as millions of records are training in a single second, and we want to handle a huge amount of data, and how this feedback loop takes the data into this database at a fraction second or a time period of time.
So, just repeat that scenario once again. You have a denial of service attack.
Millions of records are given at a single point of time.
Yeah.
And at that time, you want to predict what is actually the y dash will be.
So, what is y hat there? Y dash.
X we have the set of data.
Yeah.
And y we have the set of type of attacks we have already trained.
Yeah.
And y dash we are looking for the new type
predicted attack.
New type of attacks we want to check it out. And at the single type point of time, a lot of requests are coming, and we have to predict the new type of attack.
See, that is not a problem about feedback loop. That's a problem about handling data really quickly. Right?
But we want to extract the features of that no determined patterns also, right?
So you're asking how do we do that all in a millisecond time? Is that your question?
How can we analyze the features within a pattern or a period of time?
Yeah. So see, there are systems that have come up, right? Like for example, I don't know if you have heard of this thing called H2O. H2O just like water. Water is H2O, right? So it's a machine learning platform that allows you to deploy production grade models and has high performance, extremely high performance, right? So it's very fast, and it has a lot of inbuilt models that you can uh, use out of the box just like that, right? And you can call those H2O models from R or Python or any language that you're uh, familiar with. So you could use something like that, some platform that allows you to scale and get that performance. You could use something like that. Spark is there. Spark streaming is there for dealing with streaming data. I've never used that, but uh, that can deal with streaming data, and Spark can deal Spark along with HDFS can deal with large data sizes also. So the answer to your question, I think, is in choosing the infrastructure and the platform that allows you to handle that speed as well as size of the data. It's not got, so whatever I showed here, right, about the feedback loop, those are principles that need to be incorporated in designing your system. That will not change. What will change is how you execute that system, right? What platforms you choose, what language you choose, what algorithms you choose. Is that okay?
Okay. So I have two doubts. Can you shed me some insights about the predictive maintenance area in the real industries? Have you stumbled upon some issues over there? And can I ask the second one also? Like you said about some data drift, and is there any possibility of data drift in real industries because of all the sensors and all the PLCs and SCADAs all are fixed? I think so. I mean, I'm not
What
sure
is
about
fixed? I didn't guess that. What is fixed?
the PLCs, the SCADAs, and all the sensors are interconnected. So, is there any possibility of data drift
Yeah.
in that area? I'm not sure about it.
So let me answer your second question first. Sensor wear and tear is a common thing, right? One of the initial problems that I dealt with when I started working in data science was on the railway track. They put sensors to detect whether the track is cracked or whether the track is functioning correctly or not. Okay. What the railway company wanted was to identify whether the sensors are working correctly or not. Okay. So sensor malfunction is a big problem. Okay. So that's your first reason for data drift. Sensor quality change or sensor wear and tear. Forget stopping to work, right? That's easy to detect. Sensor wear and tear is another problem, right? As your suppose you have a pressure sensor, okay, that uses say piezoelectric crystals or something like that. As you deploy the sensor and it's been recording your pressure changes for 2 years now, the piezoelectric crystal might not be in such a great shape as it was earlier, right? Which means that the data that it's recording, the signal that it's generating may not be exactly the same kind. Its properties might have changed over time as compared to what it was earlier. Two examples that come to my mind about why data drift can happen. About application of machine learning in predictive maintenance and stuff like that. That's becoming very popular, right? I have not seen a very good demonstration of it. I have worked on similar problems, but it's not like I've not seen a state of the art come out yet in that, right? So if you take a problem like image recognition, using deep neural networks, people have come out with very, very good results. Right? So I have not seen or if you take something in natural language processing like named entity recognition or something like that, there are state-of-the-art definitions for that. Whereas I think one of the reasons is that predictive maintenance is such a broad thing, right? You can be predictive maintenance of anything. So stories have come out, but I'm not very sure how good those stories are and how to judge them. Okay, like airlines are big into predictive maintenance. You might have heard of GE, the company GE. They have a platform called GE Predicts, right? So again, I mean, I'm not sure what the capabilities of the platform are and how good it is, but people are getting interested in this a lot area because there is potential there. It's exactly like how machine learning is getting used to diagnose people, right? Like you might have read in newspaper articles and stuff like that deep learning is being used to detect skin cancer. It was a recent article, right? it's actually being used. I mean, it's proving to be very, very powerful there, and it's as good as a doctor's diagnosis would be, right? Why can't we do the same thing with machines? When machines go wrong, why can't we detect that using deep neural networks or any other machine learning algorithm? So that's becoming very popular, but yeah. What are the best applications? Who has really succeeded? That's open right now. Does that answer your question?
Yes, sir. So actually, you are suggesting like we will use some clustering techniques to identify which all sensors went south, and then we will feed that data into the model, right?
No, I'm not suggesting a machine learning technique here. Like, I'm not saying clustering techniques will solve the problem.
Okay, you're saying, okay, it might be able, right?
No, not even that. Take the machine learning algorithm out of the picture for a while, right? And what I'm saying is that machine learning techniques you might be able to use machine learning techniques to identify problem in both the sensors as well as the machine which the sensor is monitoring, which is your boiler, the example that I gave. Right? Both can be possible. But what techniques exactly will solve the problem, that very much depends on the problem. See, one of the things with data science and machine learning is that your solution not just depends on the problem, right? It also depends on the data. So for the same problem, two different kinds of data that you have with two different statistical properties, the statistical properties might arise because you captured them slightly differently, right? You might use two different sets of techniques.
Okay. A lot of academic papers are mentioning about the optimization of the machine learning architectures and the models. And can you mention about the optimization actually happening in the industry part where machine learning is used?
Can you give me an example where you heard about this optimization?
Optimization, I have seen a lot of contributions through the academic papers. Like papers, I have seen that, but I'm asking, suppose we are taking industry where it's looking for market prediction using machine learning, how they are using the optimization?
You said academic papers, but can you give me a concrete example about where you read, in what scenario you read about this optimization?
Optimization of deep learning architectures.
Okay. So let's think about it this way, right? There are two kinds of optimizations that you can do. One is an optimization that happens in almost every supervised machine learning model, maybe in some unsupervised ones also, right? Which is finding the local minima. So when you might have heard of gradient descent and stochastic gradient descent and stuff like that, which is basically identifying how close to the target can I get, right? And doing that in a systematic manner, optimizing my particular function. Like, let's take a concrete example, right? I want to say identify skin cancer using deep learning neural network, right? So I have examples of skin cancer, I have examples of no skin cancer, and I'll train my neural network to learn to identify skin cancer as good as possible, right? And I'll do that in an iterative manner using a variant of gradient descent. That's an optimization that happens in every neural network. Optimizing the neural network architecture itself is a different thing. That's another meta level of optimization that needs to happen, right? Which says that this architecture of the neural network will not be able to solve this problem very efficiently, even though the same gradient descent is happening within that, because that architecture is not expressive enough, right? Or you might say that another parallel to the architecture of neural networks is this: that suppose you are using a combination of models in order to predict something, right? And you are using majority voting or some scheme using that. What combination of the models to use and how to combine them, that is an optimization that it's not really an optimization problem, but that's a choice that you will have to make, right? You'll have to try out various things and come up with a scheme. So that's another kind of optimization. That's very similar to the neural network architecture optimization. Yeah? Yes, even neural network architectures are trial and error, right? Right now, I don't think there is a very proper scheme for identifying which architectures work.
Because I'm asking because so many mathematics want to I'm doing this paper, just doing this class, doing for optimization.
Okay.
They are not using any trial and error. They are just converting some equations or mathematical formulas. So this is the optimization part.
See, are you talking about architecture optimization?
Yes.
So that's an active area of research right now. People are I've seen several recent papers that try to use reinforcement learning to identify good architectures. So reinforcement learning, like in the case of self-driving cars, it's again creating you can think of it this way, right? It's an agent and environment model. An agent interacts with the environment, and something happens, and the environment sends a signal back, and the agent learns to do whatever it does better, right? So if you like, I've been very vague about that, but whatever, right? So several articles have come out about how to use reinforcement learning techniques to uh, identify good neural network architectures. But that's a very recent development. It's not something that's done and dusted. Where? Oh yeah. Hierarchical? HTM. Oh, I've never I've never come across it. I have heard about LSTMs in neural networks, but what is HTM? No, not come across it. It's again one of the recurrent neural network architectures, is it? Okay, fine. Any questions? Thank you then.
Thank you, Mr. Venkatramanan, for that insightful session. It has opened up our perspectives on machine learning. I request Ashok Kurian from KSUM to present our token of gratitude, Mr. Venkatramanan. Thank you, sir. I remind you again that questions are being posted with the tag DK17QZ. Post your answers using hashtag FIREPOD80 and hashtag BestofKerala2017 and do your role in making this venture known to the world. There will be prizes to the delegates with maximum reach and top 5 delegates with maximum number of correct answers. It's just a way of sharing our happiness with you. The swag coupon in your registration kit can be exchanged for your personal FAYA box at the end of today's function so that everyone back home can experience a little of what you did in here. Now we break for lunch. You can present your meal pass at the lunch counter just outside this hall. Meet you all back here at 2 p.m. Enjoy your lunch. Thank you.
Okay.